When Darwin first published his book on Origin of Species, one of the major criticisms about the theory of natural selection was this perception that it was very negative, that it was all about competition and fighting and killing other things, predation and evolving to be stronger and faster and always about competition. And there is an element of that is true and that often does apply to many species. However, there are also sometimes strategies where cooperation between individuals, even between individuals amongst different species, is the best strategy. That's the evolutionarily stable strategy, and that is what is selected for, and so we get strong cooperation rather than competition. Now, we can get mixes of both, and it can be very complicated, and so we're going to be looking at that today. We need to review some very basic concepts that hopefully you got already in introductory biology, but if not, we'll review them now. And these are ecological interactions. So I'm going to open up a Word document here just to review these. So with ecological interactions, we're looking at relationships between species. We're going to compare species 1 and what the result of that interaction is in species 1. So let's start with one you should be familiar with. So if we have a positive interaction for species number 1, and also a positive interaction for species number 2, that means that when these two species are in the same area and they interact with one another, they both do better. Their fitness levels increase, and so it's a cooperative effort. Now, when this is occurring between two species, we don't call it cooperation, we call it mutualism. Okay? So if you're not aware of that, be aware. We'll look at some examples in future discussions. So there are other possible outcomes of this. So if we have a positive interaction from species 1 and species 2 has a negative impact. Now, many people think, oh, that's predation or that's parasitism. And that's true, they do fall in that category, but there's a very general term that's even better called antagonism. So antagonism is where one of the members of the interaction does poorly because of the interaction, and one does better. Parasitism falls in this category. Predator-prey relationships fall into this category. Most herbivore and the plants that they eat fall in this category, right? Herbivore does better if the plant's there, but the plant gets eaten, so that's a negative impact for the plant. The last one that we need to know, there are others, but we won't worry about them. They're not really important for what we need to do. The other one that we need to know is when there's a positive interaction for one species and then a negative impact, or I'm sorry, a neutral impact for the other species, and this is called commensalism. So species 1 does better if species 2 is in the environment and they interact, but species 2 doesn't really matter. They do just as fine. They don't suffer or do better because species 1 is in their environment. Some examples of this are like epiphyte plants that grow on the trunks of trees. Doesn't hurt the tree or give them any benefit, but the epiphytes do better because they're higher up and they have a better environment to live in. Okay, so back to our discussion here. Sociality is a kind of a very high level of cooperation, but between individuals in the same species. So we'll come back to those species interactions, but the reason I wanted to present them now is there are many kind of similar things that occur within a species. So we're going to look at at interactions within a species right now. We talked about mating interactions and some of those things and the things that they can forces that they can exert on a population, but now we're going to look at other non-mating interactions. Okay, so first we're going to define a word called altruism. Altruism is when an organism gives up some of their resources, their health, their fitness to help another organism. Maybe a extreme example of altruism in the human race would be if an individual jumped on a grenade, sacrificed his own life to save the lives of his comrades. Right? So that's what we're talking about with altruism. And there are conditions where altruism is selected for by natural selection. And at first this seems counterintuitive, because if you're giving up your own fitness, that would seem like it would be a detrimental trait. So any new mutation where individuals sacrifice their own fitness to help others around them, that should be detrimental, and natural selection should work to remove that from the population. However, under the right conditions, because of trade-offs, it can actually be a benefit and overall provide a selective advantage for individuals that exhibit altruism. Okay? Now, we are going to call this type of interaction when individuals are helping one another within the same species cooperation. And it's similar to mutualism, but we use a different term. So, essentially, if a positive interaction occurs within a species, two members of the same species helping one another, that's cooperation. If a positive interaction happens between members of different species, we will call that mutualism. And we'll come back and talk more about mutualism in a later discussion. Now, to understand altruism, the very first theory that allowed us, or hypothesis, I guess I should say, that allowed us to understand why altruism might provide a selective advantage had to do with relationship, with kinship. And so this is called kin selection, or sometimes kinship selection. And to do this, we need to make sure that we're understanding a concept called inclusive fitness. Inclusive fitness means thinking about fitness at all levels. So we need to look at all the direct, obvious contributions to fitness, right? Like health, ability to find a mate, ability to successfully find food in the environment. Those would all be probably under direct fitness. But then we also need to consider maybe some less obvious fitness impacts that we're going to call indirect fitness. And these might include the health of your group that you're living with, right? So if you're in a strong pride, you're a lion, you're going to do better overall than if you're in a weak pride. We might also need to look at genes and allele combinations, which are sometimes tricky to measure. We might need to look at interactions between other members that are not an immediate part of your family or your social group, but do have an indirect impact on your fitness. Okay? And one of these indirect fitness costs that was not immediately apparent, wasn't discovered until much later, is called kinship selection. And this is help that you get from your family due to that degree of relatedness. Now, to do this, we need to be able to calculate out degree of relatedness. And it's a simple probability calculation. We simply need to calculate the odds or the chances that you carry the same allele as a relative. Or in other words, how closely related are you to close relatives? And to do this, we need to remember that each instance of meiosis is like basically a 50-50 chance of getting the same allele that a relative got. So it's like flipping a coin. And we talked about this in the context of how closely related you are, or how much of your genetic material you share with a full sibling. You share about 50%, give or take, of your genetic material with a full sibling. And the mathematics behind that is a little bit more complicated. Most people kind of intuitively know the 50-50 number for siblings. But what if I asked you about a cousin? How much of your genetic material do you share with a cousin, or an aunt, or an uncle? And we could go beyond that, but for the purposes of this class, we won't go beyond first cousins or aunts or uncles. We will, however, be looking at what about half siblings, or I guess you could say a half aunt, where you share a single paternal ancestor. So your grandpa is the same as your aunt's father, but you have a different mother. Okay, so we'll look at that. To do that, we need to be able to read pedigrees and then calculate out how many times meiosis has occurred to separate out two individuals. So this diagram on the left is a very simple pedigree. Squares represent males, horizontal lines represent mating events, this circle here represents a female, and lines that come down from those horizontal lines are offspring. So here we have two siblings that share the same parent. The same parents. They have the same mother and the same father. They're not twins, but they are full siblings. Okay? Now, if we wanted to figure out how related they are, we know ahead of time it's going to be 0.5 or 50%. But the math behind this is sometimes a little bit tricky. So we need to count instances of meiosis. So think about it this way. This father had to go through meiosis to make a sperm that made this daughter. He also had to go through meiosis to make the sperm that made this son. So that's two separate instances of meiosis that separate these two offspring because of their connection to their father. But remember, they also have a mother. So we need to add in the instances of meiosis. And so there are two instances of meiosis that connect one another because they share the same mother. And the math that works this is based on probability. And you're going to need to be able to calculate this for siblings, for aunts and uncles, for first cousins. So here's how it works. I'm going to make this a little bit smaller so we can see both the Word document and the pedigree here. Let's make those so they're there. Okay. Oops. Okay, so here we go. So remember, there's a 50% chance you share an allele because you share the when there's a 50% chance of an allele going into the sperm when this daughter was made, and then another 50% chance. And so the odds that they get the same thing because they have the father are 50%, 0.5 squared, right? So it's 0.5 times 0.5. That's the chance that they share the same allele because they have the same father. Okay, so we'll make that we'll put that as an exponent here in just a little bit. So let's write it out. And then because they have the same mother, there's another 50% chance for each egg that's made, and then we square it because the chance that you share the same allele from the common ancestry of the mother is also 0.5. So this is how the math works. So it's 0.5 squared. Let's make this an exponent, a superscript now, so it looks easy, or it looks right. Font, superscript. I'll do the same thing for this one here. Okay? So, that's how the math works. 50% chance each time father makes a sperm, they have to make 2 sperm, so it's 50% squared, or 0.5 squared plus 0.5 squared, which works out to 0.25 plus 0.25, so your total degree of relatedness to a full sibling is 50%. Okay? Let's do another one here. Let's go down one. Sorry. So here we go for first cousins. Now these are full first cousins. They have the same grandma and the same grandpa. You can see that up here. And so because they share 2 ancestors in common, we need to do the math for both of those grandparents. And so we would do 0.5 to the 4th power. Now why to the 4th power? Well, notice if we trace the connection back to the grandfather here from this individual here, one instance of meiosis to get to the mother, a second instance of meiosis to get to the grandfather, and then another instance of meiosis to get back down here to this other daughter, and then finally to this other grandson. So that's 1, 2, 3, 4 instances of meiosis that connect these 2 individuals to the grandfather. And then we also have to add in the contribution from the grandmother. And this is nice and easy when you do this, because if they share 2 ancestors at the same level, a grandmother and a grandfather, or 2 parents, it's always just the same thing twice. So 0.5 to the 4th power plus 0.5 to the 4th power, you do the math and you end up with 0.125, or about 12.5% degree of relatedness between first cousins. Now, if they didn't share the same grandfathers, excuse me, so here's an instance where we have the same grandmother but different grandfathers. The math is the same, but we only have to do it once because they only have that single ancestor. Okay, so you need to practice and get good at doing degrees of relatedness. On Monday, we'll practice another one. We'll do it as a in-class challenge attendance exercise, where we will calculate out degrees of relatedness for aunts and uncles and do a couple practices. So if you're not completely comfortable, if you're still not completely clear about how this calculation is done, just hold off a little bit and we'll practice on Monday. So the take-home message is that your relatives, because they share your same alleles, can benefit from altruistic behavior. So if you're helping a relative, in a way it's kind of like helping yourself, because there's a good chance that they carry your same genes. And so scientists, as they begin looking at this, realized that there was a fairly simple mathematical equation that would predict when altruism would be selected for if you're helping your relatives. And this is the equation right here. We're not going to do it quantitatively or derive any of these amounts, but you do need to understand the variables that are part of this equation. So this R is the degree of relatedness, which we just calculated. And you will need to know how to calculate that, but then we're not going to put it into the equation and then figure out whether it works. But I do want you to understand this from a conceptual point of view. The B is the benefit of the behavior. And that benefit can be for one individual or spread across an entire set of relationships. So any benefit that you get from an altruistic behavior spread across all your ancestors, that goes into this calculation as B. The C here is the cost of the behavior. And so that cost, both benefit and cost, can be very tricky to calculate, which is why we're not doing it for this class. So essentially what this equation is saying is that if the degree of relatedness times the benefit minus the cost, if that is greater than 0, then overall there will be a selective advantage for that trait, and that altruistic trait will be selected for and become more and more common in the population until eventually, given enough time, would eventually become fixed in the population. Let me give you one example. That's why we have this picture of this prairie dog here. Prairie dogs live in these colonies with their close relatives, and they have a behavior where they will warn against predators. They will stand up on top of the prairie dog mound and they'll bark. That's actually why they're called prairie dogs. They're not closely related to dogs, but they make a sound, a warning sound, that sounds a little bit like a small dog barking. And that bark is designed to warn against predators. So if there's a ferret, a type of a weasel, or a hawk flying over, or a snake, or some other predator, the first prairie dog that sees it will often get up in a high position and bark and make lots and lots of noise. All the other prairie dogs then scatter and run away to shelter, and so this one prairie dog is putting his own life at risk to warn his relatives. And they actually have done experiments where when the prairie dog is in a family group, there's a much, much higher chance that they will warn against predators. But if they're amongst non-relatives, there's a much lower chance. And so this behavior has adopted because it provides protection for relatives who have a chance of carrying your same alleles. And so in this condition, this equation worked out. The degree of relatedness times all of the benefits spread across those relatives outweighed the cost. And so this equation was greater than 0. So overall it was selected for, and we see that behavior in the prairie dogs. Under extreme conditions, this sort of altruistic behavior can evolve into a eusocial society. The definition of eusociality is complete division of roles within a society, especially in regards to reproduction. So, for instance, honeybees are eusocial. We have workers who spend their entire life just going out gathering honey and making honey. We have queen bees whose entire job is to reproduce. They never gather food. They never defend the hive. They only gather food. And in some eusocial systems, there are even more castes or social categories. Termites, for instance, will often have workers, soldiers, and kings and queens. And so reproduction is completely divided onto the kings and queens. No one else can reproduce, but there are different roles for the other castes in termite society. And eusociality is actually fairly common amongst invertebrates. We see it in crustaceans, common in several types of insects, including bees, termites. These are thrips and beetles. Some beetles have eusocial societies. It's uncommon in other organisms, although there is one example in mammals. So this is an image in the upper right-hand corner here of a naked mole rat. And naked mole rats are the only known eusocial animal. There's a queen naked mole rat, and then other members of the society are completely sterile and they'll never have the opportunity to reproduce. And at the outset, at the origin of this altruistic behavior, becoming a worker, that seems very, very unlikely to happen because that's a huge sacrifice of your fitness. If you're going to give up your potential to reproduce so that you can only help others, that seems like that should be a negative trait detrimental to your fitness and should be removed by natural selection. And probably most of the time it is. So individuals that have a genetic predisposition to jump on grenades or to put their own life at risk for non-relatives, they're probably not going to do very well if they're in high-risk environments, and they're going to die out more often than the individuals that run away and save their own lives. So those behaviors would probably be selected against and eventually be removed from a population. However, if sacrificing your own fitness, even if it's a complete fitness level of 0, if you are able to give a huge benefit to close relatives who carry your same genes, then there's a possibility that that will then be selected for and overall be an advantage. Now, for that to work long term, that then needs to be separated into different subsections of the society so that we have some individuals that then specialize as giving up their reproductive fitness, but giving huge amounts of benefit to close relatives. And amongst the Hymenoptera, which is the ants, the bees, and the wasps, this group of insects, This has evolved many, many times. When we map eusociality onto a phylogeny showing the relationships among the Hymenoptera, we see the origin of eusociality multiple times. So they seem to be predisposed towards this giving up of individuals' fitness for the help of others. And for a while, this was a mystery as to why this would be so common. It's less common in other groups, although it does pop up here and there. But it's very, very common in the Hymenoptera. And the reason has to do with a little quirk of the way that they reproduce. Now, we're not going to get into the details of how that occurs in the mechanism, but the take-home message is that female siblings share a 0.75 degree of relatedness. So instead of the normal meiotic event that you would get where you'd have a 50-50 relationship to your sister, if you're an ant or a bee or a wasp, you have a 0.75 degree of relatedness to your sister. So basically you're 75% more or less genetically identical to your sisters. And so because of that high degree of relatedness, this equation that we just talked about, this high degree of relatedness goes up, and so they can bear a higher cost of this switch to an altruistic behavior. And so when it occurs, it's more often a beneficial trait and is selected for more frequently among the Hymenoptera. So Hymenoptera show very high levels of eusociality because of that high degree of relatedness. And this is why when we look at a beehive, all of the workers are females, because they have established that paradigm in the species that allows them to help their sister, the queen, and give up their own fitness, and that was a benefit and was selected for. And the end result are these large colonies of bees with many, many female workers, all working to help and support a single reproductive female. Now, there are other things other than kinship that can provide advantages for altruistic behavior, and many of these fall into the category of an evolutionarily stable strategy. So remember when we introduced game theory, an evolutionary stable strategy is the best strategy in that environment. Whatever the rules of that environment are dictating who's going to be successful and reproduce, sometimes there's a single best strategy that works in that environment. Okay? Here's one example of another evolutionarily stable strategy. It's not due to close relationship, but due to a different characteristic of the population. We'll look at that characteristic here in just a little bit. This is blood regurgitation in vampire bats. It's kind of gross, but if you're a vampire bat, it's great. So vampire bats make their living by going out at night looking for prey items. They don't kill them, but they make a small incision and then they lap up blood. And in the environment where they live in, it's not every night that they can find an animal whose blood that they can drink. So maybe only every other night, every third or fourth night are they successful. If a vampire bat was on its own, it would probably starve to death because it needs meals more frequently than it can find. However, they are able to do well in that environment because they group together in these small roosts. And so what will happen is the vampire bats will spread out, they'll find a blood meal, and when they do, and only maybe half or less than half of the bats will find a blood meal, but when they do, they're able to get so much blood that they can barely fly. So they will basically gorge themselves, more blood than they can really make use of, but they will gorge themselves, then they will fly back to their roost. And these roosts are not family groups, they're just groups of bats that live in that area that have all found the same area to roost in. And then they will share their blood meal around the roost. And so bats that didn't get a meal will get some food from their neighbors. And again, kind of gross. If drinking blood wasn't bad enough, now we're throwing it up and sharing it with our friends, right? But for vampire bats, that works really, really well. And it only works because of these small subgroups that these bats are in. And to some extent, we can also maybe extend this to early human history also. When early humans started, well, it was actually before they would have been defined as humans because many other closely related primates do the same thing. But when our ancestors started grouping together in these small groups, maybe what we would call a tribe or a small family group anciently, and they were helping one another, there was some kinship selection there because they're often with close relatives, but also worked really, really well because there was also some of this group selection going on, which is that tribes that cooperated and helped each other more did better. They were successful. Eventually they got to a point where they were too big and part of the tribe would go out and establish a new self and compete against other individuals. And if those other individuals weren't grouped into a tribe, they'd either be incorporated into the tribe or they would be pushed out and competed against until they were pushed out or killed. And so only the groups, the individuals living in small groups were able to do well. And so that small group selection and the advantage that you get because of the fitness of your group, it's indirect selection or indirect fitness advantage, that would be selected for, and so small groups would be selected for. And so game theory can play an important role in helping us to understand these complex interactions. And we use the example on Thursday of rock, paper, scissors, a rather simple game. But if we change the rules of the game, so if we gave different amounts of points, then your strategy might change. If it was not a strict competition, so for instance, if maybe we were looking at how well does a pair of rock, paper, scissors do compared to all the other pairs of rock, paper, scissors. So your fitness would depend not only on how well you did, but on how well your partner did. And that's something that's fairly similar to mating, where your fitness depends not only on how well you do, but how well your mate does. And so then the rules of the game might change. Rather than always trying to get the best of an interaction, you might want to help your partner and cooperate because your fitness is tied up with their fitness. And so the end game is a very, very complicated question. It might change as the rules of the system change. But whatever the best strategy is to maximize your fitness, maybe even maximize other individuals' fitness if you depend on them for your fitness also, right? So for instance, if you're in a wolf pack and you are super aggressive and eat all the food and fight everybody else off and never give them opportunities, you're probably not going to do very well because your pack is weakened by that behavior. And so cooperative behaviors are reinforced when the group fitness is at risk. And sometimes we see examples of this that apply to natural systems, but other times it's really, really more complicated. This is just one more example of game theory that can be applied to natural systems also. And you'll often see this in these crime procedurals like Law and Order, where they have a couple of suspects that they've arrested and they're pretty sure that they have committed some crime, but they don't know for sure and they need to get them to confess. And so of course the first thing that they do is they separate them, they put them in different rooms. And so in this game theory scenario, the question is, what's the best strategy for these suspects, right? This is called the prisoner's dilemma. It's a classic example of game theory. So if both individuals confess, then they both might get a sentence, but because they've confessed, they might get a little bit of a lenience in that sentence, right? So they confess, they both confess, they go to prison for 5 years. But if one of them confesses, he might get a deal, right? He might, and you see this in these crime procedurals all the time, say, hey, if you cut me a deal, I'll tell you everything about the crime. So he might only be in prison for a very short time, but then his partner gets sentenced for a much longer time because he didn't confess. And so vice versa. But if both of them stay quiet, they might have to stay in prison for a short time. They might have to go to a trial, but then they might get acquitted because there's not enough evidence to convince them because neither one of them has confessed. So what do? And cops try to take advantage of this situation. They always separate prisoners immediately as soon as they can so that they can't coordinate a story and both say, hey, I'm not going to tell, you don't tell, and kind of reinforce each other. And so your behavior, your outcome of this is going to be predicted by the environment that you think you're in. If you think your partner is very trustworthy, then you might stay silent. If you think your partner is going to squeal, so I guess that's the term, right? Be a stool pigeon. If they're going to confess, you might confess and try to get your side of the story out quicker. But if you do that, you run the risk of going to prison because if both of them confess, then there might not be a deal available. So the rules of the game dictate behavior, and this is true in natural situations also. So here's an example. This is not quite the prisoner's dilemma, but is also an interesting experiment that shows this kind of helpfulness of understanding game theory. So 2 phases to this experiment, and this relies on a behavior called mobbing behavior, which is shown here, and you may have seen, where smaller birds will group together and mob a larger predatory bird to get it out of their area. So people are taking advantage, these experimenters are taking advantage of this innate mobbing behavior and using an experiment to see whether birds are assessing their neighbors and using those assessments to decide whether or not they're going to help them out and participate in this mobbing behavior. So phase 1 of this experiment, they had 3 nest boxes and they put a predator nearby one of the nest boxes. They allowed one of the nest boxes that was far away from the predator to help chase off the owl, but the other faraway nest box, they put them in a cage so they could see what was going on. The other birds could see them, but they were unable to help chase off this predator. So then in the second phase of the experiment, they put the predator near the 2 nest boxes where it hadn't been before. And what they noticed that is if they put a predator near a nest box that had given help previously, then nest box 1 was more likely to come and help. So they were basically remembering that these guys had helped them, and so they were more likely to help. And then they put the predator near the nest box that hadn't helped. Now these poor birds, it wasn't that they didn't want to help, they were constrained. The researchers did not allow them to help. The birds weren't smart enough to figure that out. Maybe if they were humans, they would say, hey, those big awful experimenters didn't allow them to help. They probably would have, so I'm going to go and help them anyway. And humans do make those sort of complex decisions, but birds don't. And so these birds would not help to chase off this predator if it was close to a nest box where they had not received help previously. So it's a complex social system with a lot of back and forth. Oops. And so this brings up an important point. I'm going to call this the why Star Trek could never be, right? Star Trek is fictional. Maybe there are lots of reasons why it would never work. But one of the reasons is, at least as far as I understand it, and maybe someday we'll be able to figure out how to get around this, but in the Star Trek universe, there are no salaries. You don't get paid for the job you do, right? Resources and energy are abundant. If you want anything, you walk up to the replicator and say, tea Earl Grey hot. Or, I don't know, you go up and say, I want an Xbox with a wireless controller remote, and it just makes it for you. So what's your incentive to work? Right? Think about this, and luckily we're doing this, you don't have to raise your hand or embarrass yourself. If you didn't have to go to school to learn how to do something, to get a marketable skill, if you could just go to a machine and it would give you everything you wanted, would you put in the sacrifice? Would you work hard? Would you study? Would you go to work every day? Right? Would you sacrifice to become a doctor or a nurse? Right? So this is why some organisms don't have social societies, and why social societies might break down. And humans are incredibly complex. The rules by which we play this game, quote unquote, are very, very complex, and so it's really hard to assess. But it's much easier in some animals that have similar behaviors. So my thought, or my hypothesis is that people living in the future, if resources were just readily available, would not sacrifice their life and go away from their family and go out into the stars. I don't know. There are other things other than money to do it, but wouldn't you stay home and say, hey, I'm going to learn how to do, play video games or go out and surf or hike all day or just spend all day talking with my family? If we didn't have to do these things that are difficult for us or that take a lot of time and effort and energy, or that where we put our lives at risk. And so you could say, oh, I just sit around. But then think what would happen if everybody just sat around all day, didn't learn those skills, didn't gain and risk their lives or risk their time and effort for some sort of a payback. Then soon the society would degrade, right? You wouldn't have anybody to repair or build new machines or invent new things. And so this is this problem with free riders. If we have a cooperative society, but there's a good percentage of the society that is not participating in that society, it puts the entire society at risk. So the only way these cooperative societies can persist if there's some sort of a reinforcement or a check against free riders. And so in our human society, we do this by a number of methods. We provide incentives for people to spend their time and energy and effort, right? So if you go to school for 4 years at an undergraduate and then 4 years of medical school, the promise is that you'll get substantial rewards, right? So you put in the time, the effort, the sacrifice, because you're going to get paid more than you would if you just say, hey, I'm going to quit school after high school and just get a job. And so that's the sacrifice and that's the reward, and it reinforces that structure, and the society stays intact. Now we could argue whether or not the amount of reward is sufficient, or maybe it's too much, but because it's there, it keeps our society functioning. Sometimes there are negative reinforcements, right? So if you do something that we think is bad for society, then you run the risk of getting arrested, getting fined, maybe going to prison, and so that limits the amount of that bad behavior, which is detrimental to society. And so we see both positive and negative reinforcements in a very complex way in human society, but we can see this in other societies also. And often these sorts of behaviors reach an evolutionarily stable strategy. One of these is competition among non-kin, non-relatives. So if two males are competing for a female, and remember we call this intrasexual selection because males are competing with males for access to the females, often these sorts of conflicts will not escalate into a full-out fight where they are running a very, very high risk of injuring one another. They'll kind of push each other around a little bit, maybe fight a little bit, but then the smaller one will run away because that's the best strategy for maximizing their fitness, because they'll have the ability to come and try again next year or fight with another individual and they still have a good chance of mating. And so we reach a stable strategy where we don't impose too many injuries and too much death on these individuals fighting with one another, but we still are deciding who is fittest and who is best, and so that is an overall fitness advantage for the population. But there are also conflicts between relatives, and some of these can result in things that from a human perspective look quite awful if we try to make a moral judgment. We need to remember that we can't apply our same moral decisions onto non-humans. So here's one example. There's conflict between parents and offspring, right? So humans have to give up a portion, well, all parents, but humans, it's very, very extreme, have to give up a portion of their time, energy, and resources to be successful in raising an offspring. Now, if they decide not to do that, they have a fitness level of 0, right? Because in biology, we define fitness by how good you are at reproducing and passing on your genes to the next generation. So you have to reproduce to have some fitness, but you have to decide how much of my time, energy, and resources am I going to give up to my offspring. And to do this, you might be putting your own life at risk. And so this question, what's the most successful resource allocation strategy for parents, can be very, very complex. And different species have evolved to fill different niches. In some species, you have a ton of little tiny babies and you provide very few resources to any one baby, and that gives you the best chance overall of succeeding. So among vertebrates, sea turtles are kind of like that. They lay hundreds and hundreds of eggs, but don't provide any resources other than the egg and the yolk, provide very little resources for the babies, and the babies are on their own. Most mammals use a very, very different strategy, and humans are maybe at the extreme end of this, where they have very, very few offspring and put tons of time and effort and resources and perhaps even sacrifice their own life for the benefit of their offspring. And that works best in the environment and the niche that they are adapted to. Now, for offspring, it's a little bit of a different question. For offspring, their best overall fitness is to take as many resources as they can from their parent, but without killing their parent, at least not killing their parent or wearing their parent out until they're able to fend for themselves. And I won't comment about how much this actually happens in human society, right? Some of you are still using resources from your parents. I'm not saying that's a bad thing. That's a good thing, and they've decided to do that and help out their children. But for offspring, the equation's a little bit different. You want to take as many resources as you can without killing off your parents. For parents, they probably want to spread their resources equally across all of their kids. If you have tons and tons of offspring and put energy into those, but then you put all of your resources into just one or a few of those, that's probably not going to be a very successful strategy. So you want to spread your resources equally across all your offspring. And this can manifest itself in sometimes unexpected ways, and we can see it coded into genes because it is subject to random mutations and natural selection. So one example is polyandrous and monogamous primates. So the prediction is that primate females will give as many resources as they can to each of their babies as they are gestating, their babies internally, right? And then maybe even post. But we're looking at this during gestation. They'll give as many resources as they can to their babies and still be able to survive. And so a monogamous primate that has a single mate can only put so many resources into the baby without putting her life at risk. Whereas if you're in a polyandrous mating system, which happens sometimes, but it's rare among primates, but there are some primate species that are like that, a single female will have more than one mate. So she'll have 2 or 3 or 4 mates that are all helping protect her, maybe providing food. And so she has more resources and can put more resources into her offspring. And so in primates that have evolved a polyandrous mating system, on average, their babies, the fetus as it's growing in the mother, is larger. So she is adapted to putting more and more resources into her baby because it gives her babies an advantage and does not risk her life because she has the support of multiple mates. And so we can see that kind of maybe unexpected natural selection occurring at the genetic level because of the mating system. And so mating system has driven fetus size in these primate species. And sometimes these interactions between relatives can seem rather harsh to us. But again, we need to remember that we don't put our human values on the society. So here are some examples. We've already talked about parent-offspring conflict. In some species, a conflict between parents and offspring arises to the point where the parents cannot survive and still provide energy and resources to their offspring. And in some species, especially those species like humans that put tons and tons of energy into one individual offspring, parents, and especially mothers, which are putting more and more resources into their offspring on average than fathers in most species, the mothers will even sacrifice their life for the benefit of their offspring, put their own life at risk. But in other species where they don't have as much energy and resources invested into each individual offspring, and they have the opportunity to reproduce again, different behaviors evolve. So in some species, mothers will actually cannibalize their babies when the conditions are bad and then just try and reproduce next year, and that's the best strategy for that species. Now in humans that doesn't work. So when I was first looking for an illustration of this principle, this is what I found. And obviously, hopefully, this is meant to be humorous, right? In humans, we don't cannibalize our babies. In fact, more often mothers will risk and even sacrifice their own life for their babies because so much of her fitness is tied up into each individual baby. And so behaviors of protecting and taking care of and sacrifice for babies evolve. But in some rodent species that can have lots and lots of babies in large litters and don't invest as much resources into each individual, in some of those, cannibalism arises. I had a student who just told me that at the pet store, they have to tell their patrons not to pet some of the baby animals because if they do, that smell will throw off the mother and she'll eat her baby. So that's a very different strategy than among primates and humans. Sometimes we get conflict between mates. So the Lion King, the entire storyline of the Lion King is based off of this new mate conflict, and it's based on what really happens in lion tribes. So when a new male comes into a pride and fights off or kills the old male, when a new male comes in, he will often kill the babies of the pride, which seems a very awful, terrible thing to do. And you're like, well, that's going to hurt the fitness of the pride. And it does, but it's an overall benefit for him because if he kills off those babies, the females are going to come back into estrus. They're going to be available for mating much more soon, and he'll have a better chance of having more offspring that represent his genes. And so that's basically the storyline of the Lion King, right? Scar comes in, kills off Mufasa. Goes a little bit different because of it's Disney and not real life, but there's conflict there, right? The male, it's better for him if he kills the babies because then he'll have more offspring, but it's better for the females if she protects her babies because she has resources invested in those babies. And so there's an equation there. How much does the female fight off the male? He's bigger and stronger than her. Does he fight him and protect her cubs to the point of putting her own life at risk? And in lions, usually the equation is no. She'll fight a little bit, resist a little bit, growl and snarl, protect her babies. But at some point, if he's very, very persistent, she'll give up and let him kill her babies because that's the best strategy historically. And females aren't doing this based on any moral decision, but they're just doing it based on what their genes say, and it's the best strategy that has evolved to maximize the fitness of both the males and the females. And then sometimes there's even conflict between siblings. I've already told you about this example of these seabirds. These are called blue-footed boobies. Yeah, quite an interesting name for the birds. But in their environment, they can only support a single chick, one egg. However, they are genetically programmed to lay 2 eggs. Now, that genetic programming evolved in a past time where resources were probably more abundant and they could support more chicks, and so they evolved to have 2 chicks. But that has changed now, and they don't have the resources to support 2 chicks. However, they're still laying 2 eggs. Now, obviously, the best solution, if you were just looking at this from a problem-solving point of view, the best solution would be just say, well, stop laying 2 eggs. Just lay 1 egg because that's all you can support. But that mutation hasn't arisen because, they're not controlling their own genetic variability. That mutation hasn't arisen, and so they're still laying 2 eggs. So that's a really bad strategy to lay 2 eggs but only be able to support 1 chick. And so if the parents tried to support their food or tried to distribute their food excuse me, evenly across their chicks, probably both chicks would die. So what has evolved is sibling conflict. And so the largest or the first hatched chick will actually peck and peck and peck at its brother or sister and even push it out of the nest until that sibling dies. And it is a waste of resources. It's not the best solution, but it's better than losing both chicks. And so remember, natural selection finds better solutions than were there before, but not always the overall best solution. So these are all examples of conflict and how these different strategies evolve based on these conflicts between individuals in the population. There can also be conflict at the genetic level where alleles can actually conflict with one another. And we're not going to get into the details of this, you just need to know the definition. So meiotic drive is conflict amongst alleles. And if this occurs, it can have a really unusual non-Mendelian impact on the population and cause some alleles to be way, way overrepresented in the population. And people are actually using versions of this to try and do things like cause mosquitoes to go extinct. And we're trying to decide whether or not we should do that. We could cure malaria by causing Anopheles gambia, a species of mosquito, to go extinct. But whether or not we should do that is different. But we have the capability to do it because we understand this form of conflict selection that occurs at the genetic level. So just know the definition of meiotic drive. And an honest signal can only be kept honest, we talked about this earlier, if there's some sort of a check, a balance. So costly signals, things that can only be exhibited if they are true, are always kept. So for instance, size. It's really hard to fake size. So if females are using the size of a mate to assess whether or not he's a acceptable mate, that's something that's really, really hard to fake. And so if a signal is costly, it will be kept honest because there's no way you can exhibit the trait without having the fitness level. But sometimes these signals are exhibited by individuals that are less fit. And so in that case, there is social reinforcement. And this happens in humans, right? Where people who exhibit bad behaviors, we reinforce by either negative or positive means, and either remove those behaviors or reduce their incidence in the population. But there are other species that do this also. So in some wasps, we won't look at the bird example, but they're basically the same. In some wasps, this really bright red front is a signal that's saying, hey, I'm fit, I'm strong, I'm the dominant wasp. And other wasps that are less fit have evolved to have black spots, and so there's a visual communication that's going on here. If you artificially enhance, so if a researcher takes yellow paint and paints over an individual that is less fit and gives them an dishonest or an artificial signal, there'll actually be increased instances of aggression against those individuals displaying those dishonest signals. And so this system has been maintained because that behavior of negative reinforcement against dishonest signals is incorporated into the population. Okay, that finishes Unit 4.4. Remember that Quiz 11, which is over everything that we did on Thursday, and then these two lectures that are posted for Friday. You need to just make sure that you take that quiz by midnight on Saturday, August 10th. Additionally, make sure that you turn in Worksheet 4. Worksheet 4, I'll post a very quick little video about how to do it with some pointers, helping you out on the last two problems, because we've already gone over the first couple of problems in class. So don't forget those things, and I will see you on Monday morning in class.